Now we come to the next point, which is a symmetrical optimum of a PI controller. That is another choice for the time constant Tn, which is not pole compensation. The question is, what is the idea behind this? Look into this table on the student paper, page 93. Here I have listed the last results. Here the I controller with control error 0, PI controller, pole compensation, all 60-degree phase margin. Here with the resulting numbers, which are not, this discussion not interesting. Look for the phase of the controller here. Phi reg is the phase of the controller at omega d. This is the effective negative phase, which makes the closed loop slow. The larger this, the smaller this. Yeah, note this is a speed indicator. So this is very slow because this is very large. Now our pole compensation controller has, I have calculated it, and I can show you on the board how I can calculate this value. This phase is smaller than this, smaller for the absolute value, you see. It's not so negative like this, so I am faster. A P controller has no negative phase, very fast. The question is, and that is what I want to show you in the next design, if we make this smaller from the absolute value here, if we make this smaller, then we can be faster here. So yeah, that is the idea. Pole compensation has a value of 36, symmetrical optimum has a value of 15, and the effect is that we are now faster. That's the idea. Can we be faster than a PI with pole compensation? Answer is yes. So we open now the paper here and say, okay, this is the next model, next type of controller, PI with, and the name symmetrical optimum can be explained in another circumstance. So wait for the declaration of this name. It comes later, but the name now should be used because this is the official name of this method. Symmetrical optimum. The idea is the controller phase at omega d is a value which relates with the speed. Yeah, I just put this on the paper. P controller phi c of omega d is 0. Omega d is 2.6 per second. PI with pole compensation, phi c at omega d is, let's calculate this, is minus 90 plus arc tangent omega d Tn, in our case minus 90 plus arc tangent. The values are, where are the value of my PI controller? The omega d value is 1.4 per second. 1.4 per second times 1 second, and this value can be calculated. Yeah, arc tangent. So what am I? Wo haben wir das? Arc tangent 1.4 is minus 90 plus 54.5 is minus 35.5 degrees, all degrees. that's the idea. If we make this smaller, not too small, but smaller, then we can be faster, because here we have an omega d now from 1.4 per second. And if you look into the table, you see if I take this value, then we get instead of 1.4, 2.0. So this is just, what can we say, 50%, nearly 50% faster. Okay, how can we do the design? The design is nearly easy. Let's look for the phase values at omega d. All phases at omega d. We have first the open loop phase at omega d, which is minus 120, given caused by phase margin is 60. Yeah. So the open loop phase is minus 120. Now this value comes from the Nyquist equation, minus 180 plus phase margin. Minus 180 plus 60 is minus 120. Okay, the open loop phase is the sum of the process phase, process actuator sensor phase at omega d, plus the controller phase at omega d. So you see this value now can be selected. That's the idea behind this. If this is the absolute value of this is too large, make it smaller. Say selection. Let's work with minus 15. Then you can see in this equation on the left side we have minus 120. On the right side we have this. If this is given, we can solve this phase equation to the value of my process phase. And then you see this is, put the minus 15 on the other side, is minus 120 plus 15, and we have minus 105. This is the way to calculate omega d, because this curve is given, and this cross point with this phase value leads to the value of omega d. Let's look into Bode plot. In the workbook, you see I have opened page 39 in my workbook, and here this diagram shows the pole compensation PI controller design. We have selected here the minus 120, go to the green curve, that is the open loop phase, and select this point, and we get here the old well-known value 1.4. Okay, you see you need now the drawing of the green curve. You need the green curve. That is additional work for the pole compensation design. Now, the next page, page 40, in the top region, you see now the diagram has only two curves, the blue process magnitude, the red process phase. There is no green curve. That's an advantage of this design method, symmetrical optimum. No additional phase curve is necessary. And now look what happens. I go now with my horizontal dotted red line at the value minus 105. Here's minus 105. And look for the cross point at the red curve. Minus 105, red curve. Cross point is omega d. And you see the value is very good. This is 1, this is 2, this is 3. Exactly at omega d is 2.0 out of the diagram, page 40. bullet plot, workbook, page 40, result, omega d is 2.0, larger as pi value with pole compensation. This was 1.4 per second. Now you see we have an acceleration. We are 50%, nearly 50% faster if we reduce this phase value of the controller at omega d. This is the selection. The result is good. Advantage of this design: no open loop phase curve has to be drawn. You have only to find a cross point at the existing phase curve of the process. This curve is available, is measured, and just look for this cross point, gives omega d. And what we of course now has to calculate is the Tn value. Tn is not selected in the pole compensation. Tn is set to the largest process time constant of the PT1s, is 1 second. Now Tn is unknown and we have to calculate the value, but note this equation is exactly the necessary equation to select now the Tn. We set Vc at omega d is minus 50, and here in this equation you see this general equation is minus 90 plus arc tangent omega d Tn, and you see omega d now is selected 2.0, and this is an equation to solve this equation to Tn. Tn is 1 over omega d times minus 90 on the other side is plus 75. So this is then the solution, tangent 75 degrees, and this gives, with my calculator I can calculate tangent 75 gives 3.73. So this is 1 divided by omega d times 3.732. In our case I have to divide by 2. So this is 1.866 seconds. Yeah, so Tn is a little bit larger than in the pole compensation case. No, Tn, instead of 1 second we have 1.866 second. But then this is the result, and the Kc comes out of the second equation of my Nyquist stability criterion, the open loop magnitude at this 2.0 frequency of course must be 1. So we put all knowledge together. Kc, the magnitude of my controller. Again, we have had this equation before, is the pi magnitude value multiplied with the magnitude of the process at this frequency. We have to look into the curve. The curve throws out a value, and omega dTn, you see omega dTn is 3.736, because this is tangent 75. Now this is tangent 75. We look into the curve at frequency 2, that is this line. This is the vertical arrow here going to the cross point of the blue curve. And we read, I think this is minus 2 dB. Minus 2 dB. Here the exact value is minus 2.7 dB at this frequency. Yeah, let's calculate this minus 2.7. Minus 2.7 dB, which is equivalent to a value that is 0.733. And if we solve now Kc, then you see Kc is the only unknown here. Omega d is 2.0, Tn is 1.866, the product is 3.736, 3.732, and if I solve this to Kc, we get this equation. In the numerator we have 3.732, in the denominator we have 1 plus 3.732 squared, this on the left side, and this is 0.733. We have now divide by this value, 0.733. Finally, this gives 1.32. In my document workbook, I have calculated exactly the same value. Here you see 1.32. So this is the result. This Tn, 1.866 seconds, and this Kc is the new PI controller with this new design. PI with symmetrical optimum. And what we have to do is look into the simulation. In my my predictors, my indicators delivers the following value. Tmax is 4 divided by omega d, so this is 2 seconds. Look for the Tmax here in the pole compensation design. We have, where is the number? Have we calculated it? Oh, we have not. Oh, Tm, here is this. Tm is 4 divided by this is 2.9 seconds. So we expect a faster reaction. Let's look in the simulation. Of course, xd of t for large times is 0, still 0, because we have a PI controller. The PI controller has an integrator, and the integrator forces the control error to be 0. So let's look into my simulation. Yeah, here we have this. Our curve is this. The blue curve here is the result of the P controller. The red curve is the result of the pole compensation PI. And I store this curve now. The next green curve will be now the new symmetrical optimum result. The gain here is 1.32. The time constant is 1.833, is it right? 1.866. And say okay. And now we recalculate the new curve, and you see the increase here. The rise time is smaller, so we are faster at the end. But here you see there is a big undershoot, and then a creeping to the final value. Not this curve, only overshoot creeping from the top. No, undershoot creeping from the bottom. Yeah, my question is now, what do you think? Which curve is better? My answer is this depends. This depends on the tolerance range. I will show you that one curve is better if the tolerance range is 5%. The other curve is better if the tolerance range is 10%. Wait for the values. We calculate these values in the next step in this symmetrical optimum design method. So, which PI design is faster? it depends on tolerance range. Look, I will do this here in this table. Okay, tolerance range 5%, plus to minus 5%, plus to minus 10%. Type, this is PI pole compensation and PI symmetrical optimum. So, and now I need these four values. Start with 5% tolerance range pole compensation, red curve. Yeah, red, green, to be clear. How large is the settling time? The settling time defines the real speed, settling time at plus and minus 5%. So start with a red curve, 5%. For this, I open the coordinate cross red curve 5%. So this is larger than 5%. It's 8%, and 5% is this point. Yeah, this is the point where the red curve goes into the 5% tolerance range and never leave it after this. So this is the settling time 2.46. 2.46 second. And I do the same with the green curve. Green curve, you see here 5%. This fits, but here you see this is deeper than 5%. It is nearly 8% down. So we have to wait until we reach the 5% here. I think this is a good point. Now, the left number here, the left number here is the time, and the right number is the y value. So this is the settling time, the 5% settling time of the green curve at 3 seconds. So you can say, okay, sorry, 3 seconds, wrong cell. No. What happens with the, so we can say, okay, for the 5% tolerance range, the PI pole compensation value is faster. The winner is pole compensation. Now we go to the 10% tolerance range. Okay, back to the curve. Red curve 10%. You see this is within 10%, so we have to go to this rise time point, 10%, and we see this is the time 1.21 second. 1.21 red curve, 1.21 second. And the green curve result comes now. The green curve result 10% tolerance range. This is within 10%. This is within 10%. So settling time at this point. This point is at the time 0.893. 0.893. We can say, okay, winner in the 5% tolerance range situation is the pole compensation, and winner in the 10% tolerance range situation is the symmetrical optimum. So it depends on the specification which of the both controllers can and should be used. Last remark. What happens? Yeah. What happens if phi c at omega d is selected to smaller values. You see, in this situation, I have selected this value to -15. Why -15? Why not smaller? Why not -1 or 2? Now, I show you what happens if this is too small. So I have calculated what happens if this is -2. We expect faster reference step response. But okay, I have calculated these values. I make it quickly and fast. The result is omega d will be, kc will be, and Tn will be. These values I just go into the curve and calculate these values without recording. The resulting values, if I calculate with 2 degrees, I have found is very near to the P controller. Kc is also near to the P controller, and Tn is rather large, is 11.01 second. So we have here P controller value. So we reach, if this goes to 0, P controller behavior and very large time constants. You should see this in my simulation, or I make a sketch what I expect. The result is reference step response. This is 1. This is 0.8, the final value of a P controller. I will promise you, or I make a sketch after simulation. So I go into this curve. I store this curve and get now the last one. I switch off this diagram, go into the PI controller value, switch this to 2, this to 11, say OK, and recalculate this curve now. And you see the behavior is very near to the P controller, and now you get very slow creeping to the final value. Now I increase to 20 seconds, and you see what happens. The time to reach the final value is now very long, because this depends on my Tn value. If Tn is too large, it takes very many seconds, 20 seconds and more, to reach the final value. So the theoretical control error is 0, but you have to wait 2, 3, 4, 5 times of the Tn time of the PI controller. So this is the case if Tn is too large, and then we theoretically here are faster, but the undershoot here, or the creeping here, is not acceptable. Yeah? So in the last word is my resulting curve is very quick. Here, there is the value, and then we get a slow creeping to the final value. And this is bad behavior. Yeah? Bad behavior. So Tn should not be too large. Should not be too large. Or in other words, if we see a PI reference step response like this, then this is an indication that your Tn is much too long. Okay, so far this is the end of the PI design, and in the next video we now want to go to the PI-DT1 design. Now we now add a differentiator. That is video 54. Video 54. Okay.